In today's lesson, we are going to learn about what is a function. Now, you may have heard this term before. It's commonly used in math, but we're going to actually look at what does it actually mean and what defines a function. So before we get into that, let's take a look at a couple of examples. So we're going to look at two figures or two images or two representations, and we want to look at what is the difference between them. So again, what is the difference between these two? Do you see any differences? Is there something that's unique about these two, or that makes one different from the other? What about these two graphs? What's the difference between them? These two grids with points plotted. Is there anything different about them? Some may be obvious, right, or common sense. Some maybe not. Right? If you can get the common sense difference, or the one that's things that are most obvious, that's great. But try to think further. What separates these two? Here's a hint. There's something that common that separates the two figures in every single example that we're going to look at in this little warm-up. What about these two? These two lines. Is there a difference? What is the difference? Well, hopefully you're able to find at least some differences. Again, whether it may be what we're looking at or what we're trying to head towards or not, hopefully you're able to at least see something different between them. The key difference was that in each pair, one was considered a function and one was not considered a function. So if you have a second, go back, watch the beginning again, and see if you can figure out which one, or take a guess at which one you think might be considered a function and what might not be considered a function. Because we're going to move on to the actual definition and then look through some examples. So what is a function? By definition, a function is a relation that for every x or independent, or for x or independent variable, there is one and only one dependent variable. So by definition, a function is a relation that for every x, there is one and only one dependent variable. Or we could say y value. So for every x value, there is only one y value. If it has more than one y value, it's not considered a function. So we're going to go back and look at a few examples of every different type, or the different types of representations of functions and relationships that we may see, to see if we can identify what's a function and what's not a function. So we have two tables of values here. One of these represents a function, one of them does not. Again, by definition, a function is that for every x value, there's only one y value. And only one. So let's look through this table of values. It looks like every x value only has one y value. However, you might find that if you look at the table at the left, it has two x values that are the same. So when x is 1, it's 6, and when x is 1, it's 7. So when we have something like that, what that's saying is that when x is 1, it's both 6 and 7. So this is considered not a function, because the x value has more than one y value. If I look at the second example, even though I have x values that have the same y value, that's still okay, because the x values are different, 1 and -1. I'm allowed to have the same y value with different x values. I just can't have the same x value have multiple y values. So I'm going to put a check mark just to say that that's okay. We're allowed to have that. So this is considered a function. If we look at mapping, so the mapping was the example where we have the different values in kind of a bubble with arrows going to what they provide. In other words, this is another way to display a table of values. In the previous example, the x value was given in the table and it told us what the y value was with that specific x value. It's the same thing here. Different representation, so it kind of maybe tidies things up or makes things a little bit easier to see. If we look at the first example, looking from x to y, or looking at the x values, so -2 gives us a y value of 4. 0 gives us a y value of 0. 2 gives us a y value of 0. The key thing here is that every x value only has one arrow going out of it. And that one arrow is going to a singular y value. So in the one-to-one example, this is considered a function. If we look at the many-to-one, when x is -1, it gives us 3. When x is 0, it gives us 3. When y is 1, it gives us 3. This is also a function because each x value only has one arrow coming out of it. So that means that each x value has only one y value. Again, it's allowed to be the same y value as long as there's only one. In the last example, the one-to-many, we see that when x is 7, it gives us both 4, 6, and 8. So this is an example of not a function. And the reason being is because the x value has more than one y value, which goes against our definition of a function. If we look at graphs, when we look at graphs, it is a little bit different. So when we look at graphs, we want to make sure that every x value has only one y value. Now, again, it might be difficult just given the graph, right? Maybe we have to take those values or those points, plug them into a table of values, and then check. But then we want to make sure that we have every single point from our graph or from our line, which may not always be easy. That's why when looking at graphs, we use what is called the vertical line test. And basically what we do is we take a vertical line. It can be an imaginary one, it could be a ruler, you can kind of move another piece of paper across your graph, maybe just an imaginary one, like I said, whatever you want. But basically, if you take a vertical line and run it across your graph from left to right, like we're reading a book, if the vertical line, intersects the graph of the relation at more than one point, so if our graph crosses, or if that vertical line crosses our graph at more than one point, the relation is not a function. So if it intersects more than one point, relationship is not a function. So I'm going to bring out a trusty little ruler here, and let's take our graph, or take our vertical line and move it across our graph. So in the first one, we go left to right, and we can see that our ruler is only hitting the graph once. Everywhere we go, it's only hitting our line at one point, or that line is only crossing our ruler at one point. So that means, the first one is a function. Let's do the same thing for the second graph. If we go across our second graph with our vertical line, again, the line is only crossing at one point. Even move it across, it's still only hitting at one point. That means that in our second example, that is also a function. Finally, if we look at our third example, and I think maybe by now you might start to see where this where this is going. If I take my vertical line and go across, I don't even need to start going further. I see that my line hits this graph at 2 points. So let's just take and draw our vertical line down so we can see by example. So I've taken my vertical line. Maybe we'll find a more clear example rather than that first point. So here, if I take a look at my vertical line that I've drawn in, I see it hits our graph relation at 1, 2, 3, and 4 points. So because it hits at 4 different points, that's more than one, this is not a function. So that is how you use the vertical line test. Right? If I go back, I'm just going to draw in a vertical line on each of them so we get an idea for what it might look like. And then we get an idea that that line is only touching 1 point every time or as we move across, except for, of course, our last example. For equations, if we're given an equation, obviously it might be difficult to see. We might have to create a table of values, or we might have to graph it, right? Because if we graph it and we visually look at it, we will be able to see what, or we'll be able to use that vertical line test we just did. So we either have to know what it looks like, come up with a table of values, or graph it to use the vertical line test. Right? If needed, you can always use Desmos. Remember, Desmos is a graphing calculator that you could use to enter your equations just to get the visual, because then by having the visual, you should be able to use that vertical line test. So if I bring up Desmos right now, right, again, hopefully you're able to get there. I'm going to enter in my two equations. So I have y equals 3x plus 1. And when I look at it, I can see, kind of behind the screen there, I can see that it's a straight line. So because it's a straight line, I know that this is a function. Or at least a diagonal line. Because if I take my imaginary line and I move across, I can see that it's only going to hit my graph at 1 point, or my relation at 1 point. If I create another graph for my second one, or graph my second equation, y equals plus or minus, so I have to see if I can get plus or minus in here. I don't see the plus or minus, so I'll have to graph two different ones. So let's say plus the square root of x. I get one there, and I'm going to graph the second one, y equals minus the square root of x. So again, the only reason I'm graphing two of them is because the equation is saying plus or minus, but I don't have a plus or minus option. Or at least I can't quickly find one on Desmos. So for sake of time, I'm just going to graph the two different versions. You can see here. If I take a look at my function, or not my function actually, because if I take a look at my graph, I can see that if I were to take a vertical line, say we just imagine the edge, you can see that we're hitting 2 points every time with that vertical line. So I'm hitting 2 points on that equation, or on that relation. So that means that the second one is not a function. And just for argument's sake, again, remembering what it looks like. So the 3x plus 1 was just a line. The plus or minus the square root of x was kind of like a sideways parabola. So again, we can see that one is a function and one is not a function, using Desmos to create that vertical, or to create a graph to use that vertical line test. If we're looking at words, this is going to be probably the trickiest type. We have to think about, does every independent, or does every individual independent variable or value have only one output? Right? You could also think of input output. If I input one thing, am I only getting one output? So for example, a tourist keeping track of the length of an Uber ride and the cost. So you can think of it, for every length of a trip, is there only one cost? Or can you have one length or one trip equal multiple costs? For sake of argument, and assuming everything is fixed, everything is standard in terms of fares, right, or things like that, so we would say that the first one is probably a function. If you want a reason why, well, one trip, or sorry, not one trip, we should say a trip, should have only one cost. Right? If you're traveling 10 kilometers, it should have a fixed cost. Right? 12 kilometers would be something different. You wouldn't say you're taking a 10-kilometer trip and it has two different costs associated with it, or two different values, or you charge two different amounts. A second example, a guidance counselor looks at the post-secondary schools a student gets accepted to. This one might be a little bit tricky because it's looking at something else, but we can think of an input as a student, and output would be the post-secondary schools. So if this was a function, that would mean that for every student, there was a singular acceptance or post-secondary school. But we know that that may not always be the case. A student can get accepted to multiple schools. So in this case, we might argue that it's not a function because a student could have multiple acceptances. So they could be accepted to multiple schools. So that means that for every input or for every student, there's the possibility of multiple outputs. So again, the main definition for a function is that for every input or every independent value or x value, there is one and only one dependent or output or y value. And we looked at all different variations or different representations of relationships, and we've found, or we've looked at examples of what's considered a function and what's not considered a function. So, just as a summary, I would like you to go through and try to come up with, again, what is your definition? So if you had to define a function to someone, what would it be? Are there any rules when determining a function? And to put down some examples and non-examples. So put down examples of what could be a function and non-examples of what is not a function. So they just kind of have like a one-page summary of the entire note. And then finally, what is wrong with this image? So obviously it's a cartoon, but if we kind of zoom in, let me kind of zoom in. It's a cartoon of a math amusement park called Function World. We have our natural log flume, we have our cosine coaster, gravitron, polar coordinate wheel, dueling hyperbolas, Tower of Terror, inverse cosine coaster. What's wrong with this image? Well, now that you've learned about functions, you should be recognizing that we have multiple roller coasters or rides that are not functions. Right? We look at the polar coordinate wheel, the dueling hyperbolas, the Tower of Terror. Some rides are not functions in what they're calling Function World. So this is an example of false advertising, right? They're calling it Function World. However, we can clearly see there are some rides that are not functions. So you would say this is false advertising. Again, just a little kind of interesting way to kind of critique someone's comic, just based on the mathematics to it, not the design or the concept. But again, the main thing from this lesson was just understanding how to define a function and how to recognize it given various representations like we just saw.